Morning, everybody. This is Tavi Burns, and he's going to talk to us about what we need to know about date and time. Sorry, date times.
Hi. So I'm Tavi. I work at FreshBooks. We do online invoicing. They paid my way here. I should probably mention them once. So what you need to know about date times. Time is complicated. I know a lot more about time and date times now than... well, you're not seeing my slides. There. So what you need to know about date times. Time is complicated. I know more about time and date times and time zones than I did 3 weeks ago. I'll probably know more by the end of Pycon. There's a lot to know. There are a lot of complicated little bits. So we've got an outline, an instant, time standards, time zones. We'll get into the Python modules that are related to date and time handling, and then also a little bit of interoperability because most of us have to deal with things that are not just Python. So Wikipedia says an instant is an infinitesimal moment in time. I think it's a fairly intuitive definition. Most people know what we mean by an instant. So an instant would be represented by, say, 10:30 a.m. here on the West Coast. And the same instant would be represented by 1:30 p.m. in Toronto, where I came from. They're different representations of the same instant. And so we define these instants with a representation given different time standards. And there are a bunch of interesting time standards, UT1, TI, UTC, POSIX, for our purposes. UT1 is universal time, and it is based entirely on the Earth's rotation. It doesn't care about time zones. It actually varies the length of a second based on how fast the Earth is spinning. The tides change that, weather changes that, the weather inside the Earth's mantle changes that, how magma moves in the Earth, accelerates and decelerates the Earth. So it's not actually a very reliable measure. But it's an interesting one, because on the prime meridian, the sun should be directly overhead at noon, by definition. Which brings us to TAI, International Atomic Time, which counts an even SI second, as defined by the atomic clocks. They have 200 approximately worldwide, and they are averaged, and also corrected for their height above sea level, because they're sensitive enough that how high above sea level relativistic effects and all that are actually noticeable. And it drifts ahead of reality, because the SI second is, on average, shorter than a UT1 second. Which brings us to UTC, which ticks these SI seconds, so each second is a very reliable length of time, but it would drift with TAI, which is what TAI does, except that we insert leap seconds, so that UTC noon, the sun is plus or minus 0.9 seconds directly overhead. And because of leap seconds, we can get times like 11:59 p.m. and 60 seconds. It's actually a timestamp that can exist, and that is one that will exist. Because the rotation of the Earth is so unpredictable, leap seconds aren't announced more than 6 months in advance. So you can't know what is going to be a million seconds in the future. You don't know what time that's going to be, because we don't know how quickly the Earth is actually going to be turning. But for 6 months, you can tell. And historically, we know what we actually did insert. Since 1972, UTC has been an integer number of seconds offset from TAI. Before that, there were fractional seconds and clock skewing and other funny things, and that was just too much work. Single integer seconds was decided to be better. The blue is unfortunately a little hard to see on this graph that I got from someone's wonderful website. And you can see the length of a UT1 day as opposed to TAI and UTC, doing it stair-stepping since 1971. GPS satellites, as you can see, also take TAI time, but plus, I think it's about 15 seconds, which is interesting. In about 50 or 100 years, the current GPS signals leap second counter will overflow. And GPS receivers will have to start guessing, did you mean 0 seconds offset, or did you mean 128 seconds offset? So that'll be fun. And really, another interesting timescale for programmers are POSIX timestamps. Most people call them Unix timestamps, but they were not standardized by Unix. They were actually standardized in POSIX. Before that, you didn't really know what you were getting. And that is the count of SI seconds since January 1st, 1970, the epoch. Except that UTC wasn't that simple, so really those first 2 years are a bit fuzzy. There are exactly 86,400 seconds per day, so that you can say, hey, I want this to happen on noon 5 years from now. You know exactly how many POSIX seconds will have elapsed. You don't know how many leap seconds are in there. And leap seconds are superimposed onto the next second. You can imagine it's very easy if you give a timestamp with 60 seconds, that really internally that just rolls over to the next minute, to the next hour, to the next day, sometimes to the next month, to the next year. And so that next second gets repeated. NTP handles leap seconds by announcing them in advance, but during that leap second, time stops, actually on the previous second. But most people don't pull NTP more than every 15 minutes, so it doesn't really matter as long as the recipient knows it's coming, and they'll know that they should be getting ready to adjust for it, either by doing a clock skip or doing a clock skew so that time runs a little bit faster or slower for the next 10, 20 minutes. POSIX does take into account leap years according to the Gregorian calendar, where every 4th year is a leap year, every 100th year is not, unless it's also divisible by 400. The year 2000 was a leap year. The year 1900 was not. The year 2100 will not be. Which is also interesting because it means that any dates you see before October 1582 don't work with POSIX timestamp styles or anything like this. If you want to try to look back in time using this formula, that's called the proleptic Gregorian calendar. And also interesting that a number of countries didn't adopt the Gregorian calendar well into the 1900s. I think Turkey adopted it in 1926. So you really have to be careful about what date you mean when you're talking about a date. They're not even as simple as you'd think. So we've talked about two different kinds of leaps. There are leap seconds and leap days. Leap seconds are the ones that keep the sun overhead at noon. And leap days are the ones that keep the seasons, the equinoxes and the solstices in the right places. And both of these are for humans because we live on the Earth, we have circadian rhythms, we like to see the sun during the day and see the dark during the night. And it's just an unstable world, so we have to deal with it in some way. So, about time zones. It used to be that every town had its own clock, and that clock was calibrated for local noon, and that meant that one town and the next town might be 11 minutes time offset, which is probably why the trains never ran on time, because nobody knew what time it was actually going to be anywhere. And so Great Britain established the first time zone by using GMT with portable chronometers, and that's how that started. There's another nice map here showing all the different time zones as of February 2012. And you can see that some places like China do UTC +8 year-round, and other places like here on the West Coast do UTC -8 in the winter, UTC -7 in the summer with daylight savings time. Interesting point of order, GMT is not UTC. JavaScript in particular is horrible for this. If you ask it for a UTC timestamp, it says it's in GMT. And those are not the same thing. GMT is the mean solar time, Greenwich Mean Time, at the Greenwich Observatory, which means it's actually a lot closer to UT1. Also historically, and GMT gives way to British summertime in England. So if you say, hey, this is sometime in GMT, and you ask, well, I want to have this meeting again in 6 months, well, what time did you mean in 6 months? Did you mean that time in GMT, or did you mean that time in BST? The meeting could be an hour off. And GMT historically was also used by astronomers who like to have all their observations on one calendar day. And so they put 0 hours at noon instead of 0 hours at midnight. And so if you use GMT, you can probably these days be sure that someone means 0 is midnight. But again, historical records are not so clear. So really, you want to use UTC because it never does daylight savings, and noon is always 1200 hours. So use UTC for everything when you're programming. In the words of Armronacher from his blog, always measure time and store it in UTC or Unix timestamps. If you need sub-second resolution, if those leap seconds are getting in your way, good luck. We can get into that in Q&A if people want to. Hopefully you don't have to care about single-second precision. Do not use offset-aware date times internally. If you can possibly help it, just avoid them. Except when you're doing user I/O. Obviously, users don't want to have to deal with UTC all the time. Particularly, they don't want to have to think about daylight savings. They want to know that when they set that clock, the calendar will still read the right time for that meeting the next day. So if you're taking user input in local time, convert it to UTC. Make sure that that conversion is unambiguous, and if it is, let the user know. Tomorrow morning, 1:30 a.m. will happen twice. you don't know which one it is. And especially if you're working on a distributed team that has people in other countries on the other side of the world, 1:30 in the morning here could be a really interesting time. You have to know when it is for the other person. They may also not observe DST. Surprise. And of course, rebase for formatting. So you get an aware date time, convert it to the time zone that you need to display, and then throw it away and don't use it again, because you don't want to use those aware ones. Naive and aware date times don't mix, and so a good thing is that if all the naive ones are always in UTC, and the ones with time zones are aware ones, then you know that they can't mix, and you can't do certain bad things. So let's get on to the Python. There are 3 modules in the standard library that really deal with dates and times, time, calendar, date, time. And there's also PyTZ from PyPy, which is incredibly useful for dealing with time zones. Time is really an interface to libc. It's like the thread module and os.fork. It provides just base interface. The time module, as far as I know, is actually implemented in C in Python. It's not a Python standard library module, it's a C module. And it deals with POSIX timestamps and struct time. Which is a Python thing. It's a time tuple, but also interfaces directly with the operating system, with the libc tm struct. Time zones are supported, but only by setting an environment variable and then calling settz on the time module. And that means that you can't do multi-threaded time zone things. You can only have one environment variable set for a process at a time. It's a hassle. You never quite know if you've set it or not, and yeah, you can't keep 2 dates in mind at the same time. Struct time is naive, but it does have an isDST flag, so that if your time zone is set to, for example, the time zone EDT5EST, or EST5EDT, it can tell which side of daylight savings you're on. For that 1 hour when it's ambiguous, but also there are places, the province of Saskatchewan, for example, is on Central Standard Time all year round. So for half the year, they are in the same times as Alberta, and half the year they're on the same time as Manitoba, the 2 provinces on either side that do observe daylight savings time. So it's important to know, should DST be set at all? Methods you can use, there's the time method, which will give you a POSIX timestamp. Python will try to give you the best precision it can, so it will actually return floating point numbers, if it possibly can on the platform. And you can use GM time to get a struct time representing the UTC timestamp, either the current instant or the timestamp that you provide. The calendar module has nothing to do with daytimes. You can use the calendar module to print up nice calendars that you stick on the wall and strike off, you know, how many days you've gone out running in the morning. But there's this one method, timegm, that will accept a time tuple and return you a POSIX timestamp. There's actually a bug open for that to move it over. I think that was for the 2732 time frame, and it was directed just because it was so much work to deprecate the old one, move it over, have it be bug compatible. And I think that was because it involved moving a Python implementation into a C implementation. That they were like, don't bother. And that's probably fair as long as people who are coming to Python in datetimes can find it. So, datetimes, the real workhorse of dealing with instance in Python. It's really the object interface. It's more like the threading module and the subprocess module. It's this nice Pythonic wrapper around these base operating system services. There are the 2 varieties, naive ones, which don't have time zone information, so you don't know what time zone they're in at all, except that in your programs, they should always be UTC. And aware ones, which have time zone information attached. They have time zone info object. They do not mix, which is nice. Unfortunately, there's still a lot of very sharp edges. So many that I'm just going to go through a bunch of things you really should do and a bunch of things you really should not do. Anything else? You'd better write some tests. So do use PyTZ. It's a fantastic thing. It ships with a copy of the Olson time zone database, which is wonderful. It means that you know that you have the up-to-date data according to the version that you pulled down. It comes with necessary helper functions to create local, aware, correct date times. I'll show you what you shouldn't do later that shows that. But you do have to update it regularly. Daylight savings time dates change, time zones change. A lot of the newer time zones are things like America, Toronto, which is, what was the time in Toronto as opposed to what was the time in Kenora or this other small town. Especially a lot of border towns may decide to use a time zone that's not the one that you would expect, given the state or province that they're in. So you really do have to update it regularly. And do make UTC-aware datetimes the easy way. You can create a datetime object and pass in a TZ info, and passing in UTC is the best way to do it. It's easy, straightforward. Now you have an aware datetime. Now you can translate that into a different time zone. If you need to make a local time, if you have the wall time and you know what time zone it's supposed to be in, you should use the PyTZ's time zone localize method. And this will give you the right answer. In Helsinki on November 6th, 5:30 in the morning, their time zone was EET, UTC +2. And as far as I know, that's what it was. Do tell localize to not guess if you really do care about that 1:30 in the morning problem. If you don't pass anything to isDST, then it will just guess. It'll guess standard time. But if you tell it none, that says don't guess, throw an exception. Ambiguous time error. There's also the non-existent 2:30 a.m. that happens on the other side of the year. And it will raise an exception for that as well. And that's a perfect opportunity to ask your user, wait, which one did you mean? Or, hey, are you in Saskatchewan? And do get an aware date time for this instant in a given time zone by saying date time now and handing it a time zone. That's actually a beautiful way to find out what time is it now in a given place. And you can get the date in a given place like that. You think, isn't that easy? Well, not so much if you're in Australia. Usually it's the next day there. So now some don'ts. Don't make non-UTC aware date times the wrong way. You'd think that you should just pass in the TZ info object to the datetime constructor. Unfortunately, the way that the API works, the time zone information object does not receive the datetime object being constructed. And therefore, you get the wrong time zone. June 1st is supposed to be summertime. But if you do this, you get -5, which is the standard time. It's the wrong time zone. Your meetings are all going to be an hour off. So this is a really unfortunate deficiency in the standard library. And short of growing a localized method, I'm not entirely sure how to do it. And certainly, I didn't see any mention in the standard documentation about this. Really, you go to the PyTZ documentation and say, no, use localize. Even better is if you're in Helsinki. What's that? HMT plus 140? No. What happens is the time zone information object, if you don't tell it anything, just has to pick the first time zone that it knows about. And Helsinki had a historical time zone that was an hour and 40 minutes off of UTC. As far as I know, nothing in the world is an hour and 40 minutes off now. Everything's in 15-minute increments. There are a few places, I think in India is on a 15-minute increment. Newfoundland, Labrador are in a half-hour increment. But nothing's like that. That's obviously just flat out wrong. Replace is just as bad. It doesn't provide any extra information for TZ infos. We have a kind of ugly diagram here. And these are just some of the suggested transforms that I went over. And I was going to say someone should make a cheat sheet, but I did. And that's linked from the presentation. When the slides go up, you can follow the link. And you can see all of the different ways that you can transform from one thing to another. So, interoperability. The world is not all Python. There's MySQL, Postgres, SQLite, and JavaScript, which a lot of us have to deal with for user interop and storing data. MySQL has a set of things, dates, pure dates, no time zones. That's fairly easy. Date times are like a Python naive datetime. It just stores a string. In fact, the SQL standard treats a lot of datetime-like things just as strings, which can be somewhat surprising. When you ask a string-like date and a string-like datetime, which one's greater than the other, and you get strange answers. And timestamps, which internally are stored as a POSIX timestamp, but are translated on I/O based on the connection time zone. So this, again, is kind of like setting an environment variable. You can't get 2 time zones worth of information out of the database. So really, you just want to set the connection time zone to UTC. Or you could use datetimes, which don't do the translation anyway. I'd probably recommend using the naive datetimes always in UTC, unless you have other applications that need to set the connection time zone for some reporting function and they don't have time zone information. MySQL does have a convert_tz function so that you can do some basic transformations and get these naive string datetime things out. But DST will bite you, and you probably don't want to do that unless you can actually store the concrete. This is Eastern Standard. This is Eastern Daylight along with your data. But now you're storing more data. Why not just store it in UTC? Postgres has a similar set of functions, including a time type that can include a time zone. That's part of the SQL standard, believe it or not, except that it makes no sense. Question?
That bit under time is way dated. That's advice from like 8 years ago. Do we recommend not using the type time with time zone?
Yeah. Yeah, that's part of the documentation. Just don't use it. It doesn't make sense. It doesn't make sense to have a time with a time zone without a date attached to it. For example, if you're on both sides of the international date line, you can get a time that shifts and it looks like it's 1 hour out when in fact it's a day plus or minus an hour. So time with time zone doesn't make sense. It doesn't store the date at all. What you probably want is a timestamp which internally is stored on a different epoch, but it doesn't really matter because, again, it's translated on I/O based on the connection time zone. So in this case, you really do just want to set the connection time zone to UTC. Postgres has an @timezone operator so that you can translate things on input and output. I imagine it will bite you for DST just like everything else will, unless you have the extra control that you get by using Python, using PyTZ. And SQLite doesn't have a date type at all, but there are 3 base types that it supports for different kinds of date formats. Text for these naive ones, real as Julian day numbers, and integer as seconds since the epoch. So really, the first and the third ones look like the best options. SQLite has some built-in date and time operators to translate between Unix timestamps, POSIX timestamps, local time, and a UTC string. It only knows about local time and UTC, and so again, it'll probably mess up all of your daylight savings things, but if you're SQLite, you probably got just a local application, and maybe it's okay to just display what's the local time for this thing that's right around now. That might be okay for you. JavaScript has date objects which do know about their time offset and the current daylight savings time setting. Unfortunately, that's all they know about. There are getUTC methods, which do return the right things. They're internally, it does know UTC, and so it'll get that part right. And you can interact with POSIX timestamps. You can pass in a POSIX timestamp times 1,000. JavaScript likes to think in milliseconds. And you can get the current Unix timestamp by dividing by 1,000. And you can get time on a date object to get that back out. So that's nice and useful, but really it's only useful for right around now because the JavaScript date objects only know about the current settings. If you say 6 months from now, it will assume that it's still standard time 6 months from now, or that it's still daylight savings time 6 months from now. It doesn't know about daylight savings time at all, except insofar as this date object has this many seconds offset. That's all it knows. So I'm not really sure what your best option is for formatting dates across time zones in JavaScript. I'm not sure most people want to ship the Olsen time zone database over a web page. Maybe you want to hit up the server and ask for that now and again. I read a whole bunch of things. This is by no means a comprehensive list, but this is a whole bunch of them. I spent a couple of weeks just engrossing myself in learning about this, trying to figure out how does this all fit together. Went down a few little paths, and that's that.
Hi, have you heard of the datetime_tz library at all?
Datetime_tz?
Yep.
I don't think so.
It's a drop-in replacement for datetime, which cares deeply about time zones, and you can't accidentally construct a non-existent value or an ambiguous value. And when you do saying things like add a day, you don't get the next day being in the previous time zone. So internally it basically recalls localize or normalize. I can never remember which one.
So PyTZ has a normalize method. So if you say, hey, add a day to this and normalize, it'll figure out what the new time zone should be.
It does that all internally in the thing, and you can. It's got all exactly the same methods as datetime, except it does the same thing when you add a time delta. You get what you expect, and if you try and add a time delta which says this is going to end up at 2:30 on a non-existent day, it raises an exception and says, hey, look, you've told it to go somewhere that doesn't exist. So datetime underscore TZ. It's a drop-in replacement. It also has a couple of nice functions like a smart parsing method, which will, like, you give it a date, you don't tell it what format it is, it will try its best to extract as much information as it can. It also understands what your local time zone on your computer is, which is actually quite hard to detect in any other method, because Python only tells you whether or not you're in daylight savings now. It doesn't tell you necessarily what your actual like time zone is. So
yeah, you can compute an offset by getting a local time, getting a timestamp, and then comparing.
yeah.
But it's
so this actually looks up your etc local time and tries and finds an associated time zone name which fits with that. And so I highly recommend that if you have to deal with local times for any reason. It makes life 100 times easier, and it has a massive test suite for dealing with these. I think we're up to like 600 tests now for dealing with going in and out time zones and all these horrible type of things.
Wonderful.
And we welcome more tests if you find bugs.
Thank you.
Okay, just a house announcement. We only have 5 minutes for questions, so keep them short.
Hi, thank you for the talk.
You're welcome.
I write Python for a company that makes software for crew planning for airlines. So the problem of time zones is it gets really hairy really fast when you consider UTC, when you consider home-based time, local time, and obviously a crew getting to an airport an hour late is not a good thing.
No.
So one of the big things that our company has had problems dealing with is we have an airport file that lists all the known airports in the world, or as many as we know about, and tries to assign an offset or some kind of time rules for each one. But we have to maintain that in a reactive mode because the laws change all the time, so we can't really know if a certain country has changed their time zone rules or the dates that the daylight savings time comes into effect. So you mentioned the Olsen database. Do you know of any other centralized repository of this kind of information?
I don't know of any other localized one. The Olsen database got taken over by IANA, I think, recently with the Astrolabe lawsuit and everything, because basically all Unix machines use the Olsen time zone database for that. I don't know of another database, but the Olsen database consists of a series of text files that contain all of the information, and also a bunch of C code that knows how to read those, compile them into a binary format, and provide C libraries with access to them. PyTZ knows how to read those then. It uses those same files. So if you've got custom software that can't use the Olsen time zone database as it stands with something like PyTZ, the data's there, and it's open and free to use for any purpose. So,
thank you very much.
You're welcome.
Excuse me. There's actually a list which...
Okay, 3 really brief comments. One is a follow-up onto that. There actually is a second one, which is the ICU database.
Okay.
The problem with the ICU database is that it's much more massive, and the interfaces to it are all Java currently, which have made it not really accessible to people outside of the Java world. But it is there, and in some ways it's more complete than the Olsen database. The second thing is about Olsen database dependent things, including both datetime and actually Postgres. Make sure that you update your software because governments change daylight saving time rules all the time. And I know I work on Postgres and we ship probably 6 Olsen corrections a year. And you have the same issue with Python. So if your application cares about time zones, make sure that you keep it updated.
Yeah. One thing that I think I forgot to mention, one thing I would really like PyTZ to be able to do is to read the system's time zone information file. At work, we have the sysadmins like in Puppet. It will set to update the Olsen database regularly, make sure it is up to date. MySQL accesses that database directly, so it gets kept up to date by system updates. And I'd love it if PyTZ could do that as well, out of the box. It does on Ubuntu and Debian, but that's by patching it, and then other things don't work quite right.
Okay.
So.
Yeah, it shouldn't be that hard to do. I know Postgres comes with that as a compile time option. you can use the system database instead of Postgres' copy of
Yeah.
the Wilson database. So it shouldn't be that hard to do. The third comment actually related to that is for the Postgres thing. Postgres actually has two data types, timestamp and timestamp with time zone, which is abbreviated
Yes.
timestamp TZ. So you want to use timestamp with time zone all the time unless you have a really good reason not to. Because even if you're just recording UTC times, then just set the database to default to UTC and use timestamp with time zone. That way, if you have to change later, you're not in a nightmare of having to refactor your whole application.
Okay, wonderful, wonderful.
Yeah.
I don't use Postgres daily, so thank you very much for that.
The question I had was, is there a Python time stamp that guarantees consistency with the Unix, with the whatever operating system thinks the time is? So you don't care about the relative times, but I want on that computer, I want the same time as other programs, operating system time.
Yeah, the time.time should return a POSIX timestamp that is what that computer thinks. On a system with libc, it'll call get time of day, which is most of the places I think Python gets deployed, except for Windows. I don't know what system call it makes on Windows. I'm not really familiar with the Windows internals. And internally, I actually went through the datetime Python module, and it calls time.time internally to get, or GM time internally to figure out what is the POSIX timestamp for now so that it can go and figure out things. So yeah, all of these things do actually ask the system what's the time going on now. All right.
Hey, I have a question.
Oh.
Is there any quick way to get location aware? No more?
Sorry, come up after.